First, for the first half of this chapter, we're talking about proportion problems. We have categorical variables. We won't be taking the average of our population. We have a categorical variable, and the entire population is broken up into only two categories. And we're going to call those, for convenience, success and failure. But it's literally completely arbitrary which version we call success and which we call failure. It's just we have two groups. Usually we call the one success that is the one we're trying to study. So please keep in mind that success doesn't necessarily mean good. Like if you're studying a new drug and you want to know, does this drug kill people? Then success would be the drug killed people, because that's what you're trying to study. And there are only two possibilities. Yes, it killed them, or no, it didn't. So here are some new letters. You want to add these to your notes. I think at the end of your notebook, where you're taking your notes, you should have all of your letters written out, because if you don't know what the letters stand for, you're not going to pass the class. It is that important. P will be the population proportion of success. Q is the population proportion of failure. So, for example, let's say, suppose somehow we know, we called up the Mars Corporation who makes M&Ms, and they tell us that 30% of all M&Ms are green. Then we have a categorical variable. Is my M&M green or not? Those are the only two possibilities. It's either green or it's not. We're going to call success green. So population is a group, not a number. On any question, if I ask you for the population, don't tell me a number. Population is the group we're trying to study, M&Ms. Success, the successful M&Ms are green. So my success rate, little p, is 30%. Well, then how would we find the failure rate? If 30% of M&Ms are successful at being green, 70% must fail at being green. So in all cases, Q, the failure rate, is 1 minus P. Okay, so somehow we know this about the population. Now we're going to try to make predictions about samples of size n. So every conclusion we come to will always be about samples of, in this case, M&Ms. Not individual M&Ms, samples of M&Ms. So we go out and we do, theoretically, an infinite number of samples of size n. So every time we do a sample, you go out, I send you all out and I say, go find me a bag of 200 M&Ms. So everybody comes back with a bag of M&Ms. Well, everybody counts their M&Ms and you'll say, well, I got 15 green in mine. I got 35 green in mine. I got 70 green in mine. Samples vary. That's sampling variability. You're going to get different samples. X stands for the actual number of green M&Ms you counted. P hat is the sample success rate. That's the percentage of green. X is the number of green. P hat is the percentage of green. So P hat will always be X divided by N. Q hat is my sample proportion of failure. And N, as always, since day one of the class, is sample size. Okay, so hats mean sample. No hats, these guys mean we're talking about all M&Ms in the entire universe. You have a P hat, which is your bag of M&Ms success rate. Okay, now, if we meet all these conditions, first, the samples must be random. You don't want to go out and buy a bag of Christmas M&Ms. Those are all green and red, right? Like, that would be a terrible sample. That would be like 50% green. Samples must be independent. Now, this word it's very complicated mathematically to prove independence. What that means essentially for us is that your act You go out and buy a bag of M&Ms and count the green. That act does not influence how many green your neighbor has. The act of taking the sample doesn't influence other samples. There are ways to break independence. If somehow doing a sample and publishing the results influences people and then they change their minds about something, then you would not have independent samples. This is going to be very hard for us to break. It's everything we do all semester, our samples will be independent. The samples can't be too large. They should be less than, N should be less than 10% of the population size, or the math just doesn't work out. But they need to be big enough. You need to expect 10 successes and 10 failures in each sample. N times P should be bigger than 10, and N times Q should be bigger than 10. Then, if we meet all these conditions, we have what's called the central limit theorem. In this case, for proportions. We'll do means next time. And the central limit theorem says that your bags of M&Ms, not the M&Ms themselves, the samples will be normally distributed. Okay, this notation confuses students every semester. This is function notation. That is not multiplied right there. That's like f of x. That says the mean of all possible samples is the population success rate. And the standard deviation of all possible sample proportions of success is square root of PQ over N. So we get a bell curve. And what we're graphing out here are bags of M&Ms. They're green rates. Some bags of M&Ms will have more than 30% green. Some bags of M&Ms will have less than 30% green. But if we average together all possible bags of M&Ms, then the average of all the bags should be 30%. And again, I can't emphasize this enough. We're making predictions about samples, not the population. So any sentence we write here is not going to say something like 20% of M&Ms. We're done there. That's completely wrong. It's 20% of bags of M&Ms.